Hello class, welcome back. In this short video, I will review the answers to the relative dating exercise I assigned this week. If you have not yet completed this exercise independently, I recommend that you do this now and only watch this video after you have attempted this on your own. I appreciate that the quality of a couple of these reproductions might have made some interpretations difficult, so I thought it might be helpful to review these together. We start with a simple cross-section comprised of 4 rock units and an igneous intrusion. And we can see that these rock units, these sedimentary rocks, are different types of rocks as they have different stippling and different patterns on each of the rock units. Here's my biggest tip. As always, our story starts on the bottom of a cross-section where we find the oldest rocks, right? Our oldest rocks are deposited first, and we find them at the very bottom of the cross-section and then move upward through our story into younger and younger rocks. So in this instance, our oldest rocks are rocks that are on the very bottom of the cross-section, are rock units C. They were deposited first. After C was deposited, we have the deposition of unit E. And after unit E was deposited, we have the deposition of unit D. Unit C, E, and D were deposited on this order, and based on the principle of superposition, we know that C was the oldest, followed by E, followed by D. And after the deposition of D, we can see that we have an igneous intrusion labeled A. And igneous intrusion A cuts through C, E, and D, and based on the principle of cross-cutting relations, we then know that A must be younger than these layers of rock. And said a slightly different way, A would not be able to cut through these layers if these layers didn't formally exist. After igneous intrusion A, we have deposition of unit B. And being the rock at the top of our cross-section, we can safely assume that B is the youngest or most recent rock to be deposited. Now, in deciphering the timing, right, the relative timing of intrusion A, it would be best to actually call in some additional observations. And here's where the principle of inclusions can end up being very helpful. So one thing to look for in identifying the relative timing of this intrusion would be to look for inclusions. Either inclusions of igneous rock A inside unit B, right, or looking for inclusions of rock unit B inside our igneous rock A. And identifying where the inclusions are would really help us just confirm the sequence of events. So specifically, if the sequence of events happened as we stated here, where A upwelled prior to B, we would expect to find inclusions of A inside rock type B after B was deposited. Our next cross-section includes several other features. I've indicated that layers A, D, and C are sedimentary rock, E is metamorphic rock, and B is igneous rock. And again, we start relatively dating this sequence, this geologic cross-section, by starting at the very bottom of our cross-section to identify what unit is the oldest. And in this case, rock unit E, our metamorphic rock, is our oldest rock unit. And rock unit B, which is igneous rock, was an intrusion of magma that upwelled into E, and subsequently, B is younger than E. Another way to think about it is that this igneous intrusion cut into rock unit E, and based on the principle of cross-cutting relations, B must then be younger than E. We could also look for some burning or heating up of our unit E, our metamorphic rock, to help us also confirm the sequence of these events. As I've indicated, unit E is metamorphic, and unit C is sedimentary. We know that there was a significant change in geologic setting between E and C. And this boundary, this contact between metamorphic rock and sedimentary rock represents an unconformity. It represents a missing piece of our story. And if we think about it, tectonic conditions that would metamorphose rock in the bottom of our cross-section here, right, in the beginning part of our story, those tectonic conditions did not exist when C was deposited because C is a sedimentary rock. It has not been metamorphosed. So we know that there has been a change, pretty significant tectonic change between E and C, and this squiggly line represents an unconformity, a missing piece of information. And often in a geologic cross-section, we represent an unconformity by drawing a squiggly line. This type of unconformity is known as a nonconformity. After our nonconformity, our missing piece of information, we have deposition of unit C, followed by deposition of unit D, followed by deposition of unit A. A is our youngest rock in this sequence, and it was laid down last. And in identifying our different sedimentary rocks, as we have here, C, D, and A, we can start start to piece together how our environment was changing during this time in history, right? The depositional setting of what results in a limestone is different than the depositional setting of what results in a sandstone or perhaps a shale. Our next geologic cross-section includes not only an igneous intrusion, but we have added a fault in layer E here. But again, we work through the process the same as the others. We start at the very bottom of our cross-section and identify the oldest event, the oldest rock unit. And in this instance, it's rock unit C. Now we can see that on the right-hand side of our cross-section, we don't see a unit C, and that is because it's under B. But if we look on the left-hand side, we can recognize that indeed there is an older unit than B, and that is C. And so that's where this story starts. It starts with the deposition of unit C. And after C, unit B was deposited. And after unit B, unit A was deposited. After unit A, we can see that igneous intrusion D cut through units C, B, and A. D cut through all of these units, and based on the principle of cross-cutting relation, D, our igneous intrusion, must subsequently be younger than all of these other units. But that's not the end of the story here, because we have a fault that actually cuts through unit D, and we can observe that through the displacement of our igneous intrusion. Fault E cuts through our three rock units C, B, and E and A, and also cuts through our igneous intrusion D. So subsequently, fault E must be younger, based on the principle of cross-cutting relations. And we know a little information about this fault, right? You guys can identify the footwall and the hanging wall of this fault, and identify that the hanging wall has slumped down relative to the footwall, and subsequently, this is a normal fault. And so at this point in time in our story, this area was experiencing tensional stress. That tensional stress was deforming this rock, right? We're adding some structural deformation here in the sense of brittle deformation and a normal fault. And the last event to happen here is really just erosion on the surface. Our last geologic cross-section is slightly more complex, with two faults and an unconformity. The first fault is at location B, in this area of the lower right-hand side of the cross-section. This line represents fault B. And fault E cuts through the entire cross-section in the left-hand side in this location. If you were unable to identify that B and E were faults in this cross-section, please don't worry about it. As long as you are able to achieve the correct sequence of events, you'll be just fine. So again, our story here starts at the very bottom of the cross-section. That is where our oldest rock has been deposited. And in this instance, our oldest rock is rock G. G is at the very bottom of the cross-section, even below rock unit C. Right? We don't see G over here on the right-hand side, and that's because this fault has resulted in some displacement. So G is below C and outside the realm of this illustration. After the deposition of unit G, we have the deposition of unit C, followed by the deposition of unit A. And unit A is this brick patterned layer of rock, right? And you'll notice that it's indicated as A over here on this side. So if you missed that, and you thought this layer of rock was layer E or B, as I indicated, you're just fine as long as you can identify that it is this layer that comes after the deposition of C. And again, that is layer A. So we have the deposition of layer G, C, A, followed by the deposition of layer F. This is layer F here. And sometimes students find layer F a little confusing because layer F does not have any patterns or stipple marks to it, but indeed this area here is a rock unit, and you'll notice that it's not included in this section of your cross section, and that is because rock unit F has been eroded from this section of the cross section. So after the deposition of F, we have fault B, which cuts through all of these layers. Fault B cuts through layers C, A, F, even cuts through layer G. And based on the principle of cross-cutting relations, we would know that fault B is subsequently younger than all of these layers. And if you look at fault B, please ensure that you're able to identify that this fault represents a normal fault, where our hanging wall has slumped down relative to our footwall. So at this point in our story, this area was experiencing tensional stress, and it deformed brittly by a break in the rock and a subsequent movement, our normal fault. After our faulting, we had some erosion, and this squiggle line in this area represents an unconformity. It represents a boundary between layers F and the layer above the unconformity. In this area, we were experiencing erosion. That's what removed layer F, the rock layer in this area. This type of unconformity is known as a disconformity, right? We have flat-lying strata underneath the erosional surface and flat-lying strata above it. So right here, we're seeing a disconformity. After this erosional event, we had the deposition of rock unit H, the deposition of rock unit D, and the deposition of rock unit I. In this fashion, and based on the principle of superposition, we know that H was deposited before D, and D was deposited before I. And after the deposition of I, we have another fault. This is fault E, and fault E cuts through all of these rocks. Based on the principle of cross-cutting relations, it must be younger than all the rocks it cuts through. E is another normal fault. The hanging wall has slumped down relative to the footwall. So we have another fault here, fault E. And our last event is erosion of the ground surface. And that erosion has removed rock I in this location. In identifying the different types of sedimentary rocks in this sequence, we're also able to start to piece together how the environment was changing here, right? The depositional setting, which yields a limestone, is very different than the depositional setting that yields a sandstone and a shale. So within this sequence of events, this story, we're able to not only identify times of tectonic stress, in this case tensional stress, but we're able to identify a change in the environment. Are we coastal or deep marine? I hope this was helpful in your understanding of how to relatively date a sequence of events. And remember, always start at the bottom of your cross-section. These are your oldest events, or what happened first in your story, and work your way up your cross-section to the top of the cross-section, which are your youngest events. These are the events that happened most recently. And don't hesitate to reach out if you have any questions.